This definition for the basis vectors. So we have to find out this term, right? We don't know what that term is. That's new in this equation. So we use the definition of the instantaneous eigenstates. Take the time derivative on both the left-hand side and the right-hand side. Okay. So I'm skipping those algebraic steps. So take the time derivative on this side and on the right-hand side and project it again onto the CL or epsilon L. And when you do, you find, so after a few steps, take time derivative and then project onto epsilon L from the left-hand side, then you find that this equation reduces to this one. For L not equal to K. So this is the expression for L not equal to K. And the reason is that there is an extra term which will involve the projection between epsilon K and epsilon L. And so when L not equal to K, that term will vanish when you do that. So substituting that, we see that the CK dot or CL dot is equal to minus I epsilon L over H bar CL minus, now this term which is over here. And so this term we can write it in two parts, the part where K prime equal to L, right? And then the parts where K prime not equal to L. So the part where K prime equal to L will give us a term right? So when K prime equal to L, we get that CL. Then the term that we just showed, when K prime is not equal to L, which is this, you have this term here, epsilon L d over dt epsilon K prime, will give us this term which looks like summation over K prime 1 over epsilon K prime minus epsilon L times epsilon L d over dt of epsilon K prime. And this is for K prime not equal to L. Right? Oh, sorry, dh over. And so you can see that CL dot now is almost an eigenstate, because see the terms that multiply CL, right? There is a term that has did I miss a factor of I somewhere? Well, the point is that CL doesn't depend on any of these other, CK prime, that's right. So you can see that the transitions from out of the state L, remember we prepared the system in the state L, right, epsilon L, and any term that causes you to go out of epsilon L, that is, that does not depend on just the coefficient CL, right, is going to cause the transitions out of that state and destroy the adiabaticity. So the adiabatic theorem is essentially equivalent to neglecting this entire term over here. Okay? That's what we are doing. So when can we do that? If you look at that Hamiltonian, you can see when this matrix element is small compared to the difference between the energies of these instantaneous eigenstates, we can neglect this term. Right? So if I were to integrate this equation, this guy will be multiplied by dH over dt times some time over some time that I do the integral, right, approximately. So what we want to say is that for a time t, or delta t if you like, where the term changes, if it is sufficiently slow changes in h, so that this matrix element dH over dt epsilon L k prime times some delta t, right, is much smaller than epsilon k prime minus epsilon L. Essentially the magnitude of that, right? That's what we care for. Then we can neglect this term. And in that case, then we can look at the evolution of CL dot now in this adiabatic approximation. So IH bar CL dot is approximately equal to now epsilon L of t, right, minus this interesting term which you may have encountered before. Right? So if I neglect that last term, set it equal to 0, then this is all I'm left with, and you can see now that CL only depends on the derivative at any time CL only depends on the value of CL and not on, say, CK, for example. So the system remains in the eigenstate that it was prepared in, except for these factors. And the first factor here is pretty straightforward, right? If a system had some eigenenergy epsilon L, then it will accumulate a phase at that rate, epsilon L. But the second factor is quite interesting. Does anybody know what the second factor is? What it represents? Did you know about this second factor that happens in evolution over some time t? Notice that this phase factor over here, right, sort of represents how much the basis state itself is tilting with respect to the original one, right, at any time. So this is what is known as a geometric phase or a Berry phase. Okay, so I don't know if you guys read about Berry phase in grad quantum. Did you ever encounter Berry phases in grad quantum mechanics? Anyone? Berry phase? No? Okay. So what I'll do is I'll give you reading. So if you look at Sakurai, for example, there's a nice treatment also of the same thing, but in a more generalized fashion. So maybe I can give you that, or maybe I can write up some notes for you. But the point of this exercise now is to show you. So let's now do, like, say, a two-level system and an adiabatic experiment or adiabatic passage in that. And this guy here is what we call the dynamic phase. Okay. Because over any time evolution from 0 to t, you can see that the system will pick up a phase which is proportional to its energy. Okay, which makes sense. That's what dynamics does, right? It picks up a phase factor that is dependent on the energy of the system. Okay? But this guy, as you can see, depends on something more interesting. It depends on the rate or the tilt of the basis vector with time projected back onto the original basis vector. Okay? So if you take it on a circuit, for example, and this is the most famous examples, right? If you take a two-level system and you prepare it initially in some superposition state, right? Prepare it, say, in the 0 plus 1 state, okay? And go back to the block sphere. Let me sketch it over here. Make sure I say this right. So suppose I take a system on the block sphere, okay? This is the origin, this is the axis, and let's say that at time, make sure I say this. Okay. Let me prepare at time t. Let's say that this is the, and we know that the other that we can represent, say, the effect of the application of, say, some microwave or some omega and delta, right? Those are the Rabi and detunings of this microwave pulse, then or microwave field that we put on it, and we prepare the system, let's say, initially with a pi over 2 pulse. So initially I start with the system in a pi over 2 pulse, so that the system has been prepared in, say, a superposition of 0 plus, say, 1. Okay? So initially the state vector might be pointing like this, okay, along this axis. Okay? And now I apply along with this some microwave field, okay, which has some Rabi frequency omega and delta, which are functions of time. Let's, for example, fix the delta of this extra. This is another microwave field. Okay, this is an extra microwave field. Call it the geometric field or whatever you want to call it. It's an extra degree of another microwave or laser field that you apply to the system. And this guy now, what I'm going to do is I'm going to phase modulate it so that initially the effective Rabi frequency or the effective magnetic field is pointing along this direction. Okay? And then, if you think about the state vector, at every point, remember, it has to adiabatically follow this system. So if I take it and I prepare this entire, if I take the effective Rabi vector, which is basically given by this ratio between omega and delta, and the total value is square root omega squared plus delta squared. So this is some, if you project it on here, it is some omega with some components, omega x and omega y, right? That is determined by the phase of the microwave. So by altering the phase of the microwave, I can take the entire system along this path as I take it, and what the Adiabatic Theorem says is that the system which I prepared initially in this eigen state, which is 0 plus 1, should follow along with this evolution, right? As time goes on, the system should eventually come back to the same state with some phase that has been altered to it. That is, you have picked up some phase, right? which of course implies some tilt in the xy plane, right? Because you remember that any state in the Bloch sphere can be written as having some components along the x and y axis, which depends on the phase, the superposition state of the. If initially it was in the x-axis, if it picks up some phase phi, then it's going to be tilted by that extra phase after it comes back. And so what we can do is, for example, we can arrange, for instance, that if this dynamic phase can vanish, right? If we correctly do the evolution with this omega and delta, now we would have expected that the system would come back to the same phase. It should come back as an x point, like it should be pointed along x again. But what this is arguing is that in fact that will never happen, because there will always be this corresponding geometric phase. And in fact what Berry showed is that this geometric phase is dependent on the cone, this solid angle of this cone that is subtended by this evolution, by this entire cone at the origin. Okay? So it has no dependence really on how you do this process, how exactly you bring it back along the curve. You can do it, in different ways. For example, you could have, done that. Okay, that could have been the path that omega and delta followed, and all that matters at the end is the angle that is subtended by this cone that corresponds to how much this geometric phase, which you can call say beta, is a geometric phase, which is the amount by which the state vector. Maybe I should use different colors. These arrows represent the evolution of omega and delta in this Bloch sphere. This arrow is sort of my representation of what the initial and the final states of the system are. Because remember, we prepared it initially along the x-axis, so it starts out along the x-axis, and I'm saying after it comes back along the circle, the state vector has rotated. Okay? It's no longer along the x-axis. One component of that rotation is the dynamic phase, which is just purely due to the change in the energy over time. But we can, over a full circle, ensure that this dynamic phase component goes to 0. Okay? But what this Berry phase or geometric phase says is, there will always be a corresponding geometric phase that the system picks up, which is governed by the solid angle of this cone that is subtended at the origin. So I can give you some more details. You can work out the math of this in Berry's original paper, which is also sort of nicely done in Sakurai in a last chapter or something like that. So I'll move on from here. But if you have more questions, so there have been experiments now that have been done with systems. So, for example, initially these Berry phase experiments were done with photons, but they have now been extended to both superconducting qubits and spin qubits. So, in fact, in my group, we did a similar Berry phase experiment with spin qubit in diamond. So, which shows that it all really works right down to like a single spin level. Okay, and why is this interesting? Because this, for example, allows you to control the phase or the rotation of the state vector irrespective of the exact path that you might take. It's less sensitive to any kind of noise that might happen along the path. So maybe this is a more resilient way to do quantum computing or quantum information processing with qubits by using the geometric phase instead. Now there are some issues with this which we'll try to discuss later on in the class, but for now I just wanted to leave it at that. So that's the geometric phase, and you should know about it. So let's, and also of course you can try to alter this conditions of the adiabatic approximation, because of course we have to make sure that the system never goes out of the adiabatic approximation. Otherwise we will start getting terms that make the system, that break this nice sort of picture, and so then you'll have to worry about those issues. So you have to always be careful about that. It also leads to a whole field of adiabatic quantum computing, this Adiabatic Theorem. So I think it's important to have some knowledge about it if you're interested in those kinds of things. So what I want to do now is go from the general this general adiabatic theorem, and let's discuss a specific case which we already did a little bit, which is adiabatic passage in a two-level system. Okay, we already introduced it a while back, but we didn't do the math, or we didn't follow through all the details of it. So let me do that as an example, right? Because then you'll really understand that, and you'll also understand where the adiabatic theorem starts to break down. Okay, or what happens when the adiabatic theorem starts to break down, and what conditions do you have to follow. Okay, so we're going to consider adiabatic passage in two-level system. Adiabatic system. Okay, so we had the Hamiltonian. Right? This is in the rotating wave approximation and in the rotating frame. And what I'm treating as my parameter is the delta now. Okay? So remember, in the adiabatic theorem, we always assume that the Hamiltonian is a function of some parameters. Of course, I could make both delta and omega as parameters, but I'm just treating, say, delta as a parameter and omega is going to be a constant, for example. Okay? So we are considering that situation. So we've already shown that we can go to the dress state basis, right? And in the dress state, h, which is now a function of time, right? Because of the delta of t, is represented by the two eigenstates plus, and with the energy epsilon plus, and another state minus with an energy epsilon minus. Okay? That's what we showed earlier in the class a few weeks ago. Before I erase it, just notice sort of again what it is that we usually look at. We want to know that the adiabatic theorem is followed, or the adiabatic approximation is valid when this change in the Hamiltonian on the off-diagonal elements. Look at these are off-diagonal elements, right? For any individual state L, we look at the rate at which the change in the Hamiltonian causes transitions from L to some other state K prime. And we want this rate with which these transitions occur to be much smaller than the splitting between the two energies of this instantaneous eigenstates. So we'll apply that first, and then we'll show how that works in the full system. So first we'll apply the theorem to make sure, and then we'll so the sketch, once again I remind you, this is the sketch of the system as a function of delta over omega, right? So you start on the negative side. So of course in the bare state, which is, okay, so I'll sketch the bare state, actually it's a thicker white line, that is the state 1, and then this is the bare state 2, right? Sorry, things are not very straight on the board. And then we have the dress states. We have the plus state, which starts that. We have the minus state, which starts like that. Okay. So if initially I start with everything far detuned to the left, so if delta of t starts out negative over here, then this state is almost equal to the minus and the plus state are almost equal to each other. So the minus state or epsilon minus state and the 1 state are almost equal to each other when you're far detuned. So I can represent that as 1, okay, which is almost equal to minus sign, the minus state, and then as I sweep delta over to the right hand side, if I meet the conditions of the adiabatic approximation, and you can see the conditions of the adiabatic approximation are that the change in the Hamiltonian, right, h of t, dh over dt, should never exceed the splitting epsilon plus minus epsilon minus, and that splitting is minimum at this point, at 0 dt. Okay? So as time goes on, we will continue to stay in the state minus until we reach the other side, and at that point the system will go into the state 2. Okay? And so this is stable against things like fluctuations in the laser frequency, fluctuations in omega, the Rabi frequency, and so on. So we use this in situations where we may not have full control over those variables, or we think that there may be some noise or something that could mess up our control of those variables. Okay? So the key condition then is that the sweep rate of which is going as 1 over t of the frequency, right? This is the rate at which should be much smaller than the splittings between the eigenstates with some factors of h bar. H bar over here. Okay, I may get that wrong. Just you'll have to fix that. Okay. And this splitting, this is the adiabatic theorem, right? I'm not redoing it. We'll come back to this in a second when we actually derive it again for the two-level system. But the point of this is now that this guy is minimum, right? This guy is a minimum at the point delta equal to 0. So if I set this equal to omega, and at this splitting, the splitting is omega. Okay, when delta equal to 0, epsilon plus minus epsilon minus is exactly equal to omega. Okay. So as long as the sweep rate h bar over t is much lesser than omega, the Rabi frequency, or equivalently omega t is much greater than h bar, then you are in good shape. So that is our condition. So that's it. That is, now we have a more numerical or a more quantitative understanding of how an adiabatic passage experiment should be set up. You want to make the sweep rate, when you go from negative to positive, to be following this condition always. Okay?
What's the big T again?
Big T is the rate with which, or the, let's say it's the sweep rate, right? 1 over the time, where time is the rate, the time that it takes to sweep from 0 up to, from minus infinity to plus infinity, for example. Okay? Okay, so now let's derive that a little bit more, even more, in more detail. So this just gives you the immediate, so you know how to do this experiment now. If you had to set it up, you have to follow that condition. Now we can derive it for the two-level system. So again, if h equals minus h bar delta 2 minus h bar omega over 2 of lambda omega percent. Then the Eigen values epsilon plus minus is equal to A divided by H bar is equal to minus delta of T over 2 plus minus 1 over 2 square root delta squared plus omega squared. Right? This was the dress state basis. And we also can write down that epsilon plus is equal to cosine of theta times 1 minus sine theta 2 and epsilon minus equal to sine theta 1 plus cosine theta 2, where this theta basically is on this triangle, represents the angle between a triangle that has its sides as omega over 2 delta and then of course square root omega over 2 whole square into this delta square. Okay? So, yeah, I think that's it. If I now write the system aside of P, basically all I'm doing now, if you're a little bit confused, sorry if I didn't explain this, is I'm taking the derivation I did for the adiabatic theorem, that was in the most general case, I'm repeating it for the two-level system, so that you can exactly and explicitly see which terms we are neglecting in that Hamiltonian, and then I'll be able to use that to very rigorously derive what I just derived there. See there, I just made the analogy with the adiabatic theorem. I just said, as long as I satisfy this condition from the adiabatic theorem, I'll be correct and everything will work out. Now I'm going to show you that that's indeed true by simply re-deriving the adiabatic theorem for the two-level system. So there's nothing new what I'm doing, I'm just following the same steps, but I'm doing it for the two-level system because then it becomes much more sort of, specific, like you can actually see how every step of that works. So the derivation is almost the same as for the as for the general theorem. So I've expanded psi of t in terms of the dress states, epsilon plus and epsilon minus, and now I apply the Schrodinger equation. Okay, I'm going to just skip all those steps. So IH bar d over dt psi is equal to 8 psi, and when I do that and I apply that, each of these guys has some time derivative, I'm going to end up with two equations. Okay. IH bar C plus dot of t is equal to epsilon plus of t, C of t, C plus of t, minus C plus of t. Okay, maybe I should write this on the next board because it's going to be a long equation. IH bar C plus dot. Sorry, I erased the Schrodinger equation, but you know what I'm doing. I'm just taking that, putting it in Schrodinger equation. Epsilon plus of t, C plus of t, minus C plus of t, epsilon plus d over dt, epsilon plus. So remember, when we did the adiabatic theorem and we took the bra with epsilon plus, there was a term where epsilon plus and epsilon plus, that is the L equal to K term, and then the term which represents all the transitions out of L equal to K, in which case, in our case, for a two-level system, there's only one such term, because there's only one other state to which we can have transitions, and that is the term which goes as epsilon plus d over dt epsilon minus. Okay? And IH bar C minus dot of t. So no approximation so far, right? Everything is correct. So in the adiabatic approximation, we drop this. Then we are left purely with this set of equations. Okay? So in the adiabatic passage experiment, so adiabatic passage, and then we'll be able to see again when this approximation or the adiabatic passage breaks down. Right? So for adiabatic passage, t equal to 0, I start at delta equals some minus a times mod omega, okay, where a is some number which is very large, right, when I start out at time t equal to 0, and then at time, whatever t equal to large, some time capital T, it goes to delta equals plus, say, a over omega, okay, and at time t equal to 0, we also assume the system started at, say, in the one state, which is identical with epsilon minus of 0. So in that case, basically what I'm saying is that C minus of 0 equals 1, C plus of 0 equals 0. So I can substitute that into these equations. I've already dropped those terms which are the adiabatic in the adiabatic approximation. So all I'm left with then is this simple equation. Psi at time t equal to capital T is equal to C minus at time t times epsilon minus of t. Right? Because when I integrate this system, then I end up with the coefficient at time C minus of t, and everything has stayed in epsilon minus because I neglected those terms that take me into C plus, for example. Okay? And C minus of t then is now exponential minus I beta d plus I beta g. Beta d, as I've called it, the dynamic phase, is 0 to t, epsilon minus prime, dt prime, over h bar, and b geometric phase, 1 over h bar, which represents as epsilon minus evolves, it ends up having some angle with respect to its final term over here, which is its original equation over there. So its original angle in the basis states. Okay. So if I write down what this can be, if I want to write it now in terms of the parameter which is actually being swept, then I need to write this as from delta at time 0 to delta at time t. I'm making a transformation of variables. So epsilon minus of delta divided by h bar times d delta over the derivative of delta with respect to dt. Right? So I just transform variables. So instead of looking at the time evolution, I've transformed it into a variation over delta, because that's the one that I'm sweeping in the actual experiment. So now I can I erased it, but we had expressions for epsilon minus in terms of delta. Remember, the epsilon minus was just essentially I can write it again. So epsilon minus was minus h bar delta over 2 minus square root delta squared or delta squared plus omega squared. Or maybe there's omega squared over 4, I can't remember. But whatever. So there's some dependence on delta right there, and so we need to just basically evaluate this guy, and that gives you the dynamical phase in the experiment. Now we can ask, what is the what happens when this adiabatic approximation breaks down? Okay, that allows us to tell when or what sort of, remember when I originally set up delta sweeps from say minus a omega to plus a omega. So that would be what I would put for delta of 0 at delta at time t over the time t on these limits. And then I have to evaluate this adiabatic approximation, that is the terms that I draw. I want to understand what happens to those terms. Okay? Okay, so that's fairly straightforward. So I won't go through the math. Math is just evaluating these derivatives, basically. So now I have to look at these terms over here and evaluate them. So, and that's, as I said, it's not too hard because we know what these epsilon minus states are for the two-level atom. So let me erase this part. So if I go back, let's say I look at epsilon plus of t was given by some cosine theta 1 minus sine theta 2, where theta was, on this triangle with omega over 2, delta, and the hypotenuse, right? And so essentially now I have to calculate that last term in the Hamiltonian, oh sorry, not in the Hamiltonian, but in the, So I have to calculate d over dt of epsilon plus of time t, and I have to find the projection of that on epsilon minus at time t. This is the term that we dropped earlier, okay? So the breakdown of the adiabatic approximation will occur when this term is not small, basically, right? That's what we have agreed. And in fact, we know what it has to be comparable to. Sorry, I wrote this for C minus, but you can also write it for C plus, right? So for C plus, instead of this, it'll be just this. No, actually, I'm sorry. That's right, because I just erased it. But that term in the differential equation was basically the change in epsilon plus projected onto epsilon minus multiplied by C plus is the term that we have just drawn. So we want to look at this term, and what we are comparing it to is the dynamic phase for C minus, right? So C minus evolves according to the dynamic phase epsilon minus. So when this term is much smaller than epsilon minus, then if this is much smaller than epsilon minus, we know that it will be we can neglect this term in the evolution. Okay. So I'm going to just skip the steps. Basically, you can just show after some algebra that this guy here is epsilon plus of t omega divided by 2 omega squared over 4 plus epsilon plus squared times delta dot divided by square root delta squared plus omega squared. And so when I set that to be much smaller than the epsilon minus, I end up with implies when I equate these conditions, I get delta dot. Remember, we are trying to see what this delta dot is. Has to be much smaller than 2 omega squared over 4 plus epsilon plus squared divided by omega times square root delta squared plus omega squared. Okay, just some algebra, not going through the steps. So when we sweep delta from minus a omega to plus a omega, okay, delta dot then, right, delta dot is going to be approximately 2 times a omega divided by t, right? Over the time t, I'm assuming some linear, just a linear slope for delta. So delta dot will go from minus a omega to plus a omega over a time t. So that's the slope, delta dot, 2a omega over t. And then on the right hand side, we can look at this term. We see that this term is minimum, right? We want to always keep this smaller than this guy. This guy is going to be a minimum when delta equal to 0, right? When delta exactly equal to 0, right? Because delta is the only thing that's changing in that term. Well, epsilon plus is also changing, but it's changing dependent on delta. Then this term will be smallest, or you can plot it, whatever, you can do anything you want, and you can see when it is smallest. And you'll see that it is smallest when this delta equal to 0, at which point epsilon plus, when delta is equal to 0, epsilon plus just becomes equal to omega over 2. So substitute all that back here, you get 2a omega over t must be much smaller than omega squared. Okay? And when you get that, you get that omega t must be much greater than 2. So a similar condition as we derived from the geometrical picture, but now we have actually derived it from looking at the algebra of this breakdown in the adiabatic approximation. So this is how you would go about in a real system that was not 2 levels. You could do all this again algebraically, or have your computer do it, or whatever, to see when the adiabatic approximation would start to break down. Okay. Did that make sense? The derivation? I didn't want to lose you in the algebra part. The basic physics is to look at what happens to those extra terms in the evolution, those terms that we have neglected in the adiabatic approximation. But also you can say if the adiabatic approximation is valid, then the solution is very simple, right? If you start in the state minus, you stay in the state minus, and you keep evolving with some phase factor, and that phase factor is just dependent on the dynamic part and the geometric part. Okay? And so it's an easy way to understand what's going on in the system without actually solving the system. The system is basically, stays very simple in this way. Okay, so we've done this both with the geometric picture of the states, and we've done it with the algebra. So now, let's see, in the last few minutes, I thought I'll introduce another interesting adiabatic passage system, which is a 3-level system. Then we can move on to quantization of the electromagnetic field. Okay. All right. Okay, we're going to do 3-level system now. Now I won't be doing so much algebra, we're just going to reason by analogy with the 2-level system. So there are different types of 3-level systems that one can consider. They go by different sort of names in our quantum optics. Typically every system can be written as, and in fact actually there can be transformations between all of these, but this is the so famous V system. Okay, so we have one ground state, one, which is connected to 2 excited states by 2 different optical fields. Okay, so this is the V system. Then there is the lambda system. This is connected again by 2 laser fields. So this is lambda, because it looks like a lambda. And then there is the ladder system, or cascade, as it is called. And in fact, it turns out that by different transformations, basis transformations and so on, you can sort of make these systems all equivalent to each other. So in a realization in atomic systems, for example, you could have, we have already looked at, for example, systems where you have transitions from J equal to, say, 1, Mj equal to 0, and plus minus 1 in the ground state. This is the ground state. And then it goes up to J equal to 1, Mj equal to 0, plus minus 1 in the excited state, right? So the ground state is, let's say, degenerate, has minus 1, 0, plus 1, and then you have minus 1, 0, plus 1 up here in the excited state. And so for example, with a laser, which is, say, sigma plus polarized, right? We would go from minus 1 state up to 0 by using a sigma plus polarized photon. And we could use with sigma minus polarized photon, we could go from plus 1 up to 0. And this state, of course, this transition is prohibited by angular or dipole selection rules. So we only have to, if we send in sigma plus and sigma minus, we don't have to worry about a combination of them addressing the transition 0 to 0. Okay. This is in atomic systems. For example, in my system, NVs, there is an ms equal to 0 and an ms equal to minus 1 and plus 1 state in the ground state. This is spin quantum numbers. And then you can have a V system, which is like this. So this is a sigma plus transition, and this is this is a sigma minus transition, and this is a sigma plus transition. So that we can, again, we could use, for example, different selection rules or other ways to address these states. Anyway, so these show up in many different cases. Superconducting qubits, for example, you will have a couple transitions, right? Ground state to the first, what do you guys call that? The orbital level or whatever? I don't know. E state, okay, yeah, exactly. So ground to E, and then there's one more which is slightly detuned from this one. And if you did this, you would get a 3-level ladder system in superconducting qubits. So in different qubit systems or atomic systems, whatever, you can have all different kind of excitation pathways. Okay. The Hamiltonian now that I'm going to do is for a lambda level system. And we're going to use all the intuition we built up for 2-level atom to directly write down the Hamiltonian in the rotating frame and in the rotating wave approximation for this system. So here is lambda level system, state 1. There's another state 2. There may be some splitting between these guys, okay, which I'm keeping as, say, omega naught, omega 1. And then there is the excited state 3, which is at some frequency omega naught, like before, from the, say, the state 1. The state 1 is at 0 energy, right? And then I have 2 optical fields. This has Rabi frequency omega 1 and laser frequency nu1, and this guy has Rabi frequency omega 2 and laser frequency nu2. Okay? So we can see that this guy, for example, is detuned by delta 1 from the transition 3. This guy is detuned by delta 2 from the transition 3. So when we go into the rotating frame with these 2 levels, how should I redraw this entire system in the rotating frame? What will happen to the states 1 and 2 in the rotating basis?
So excuse me, what's the delta 1 and delta 2?
Delta 1 is the detuning of laser 1 from the excited state 3, and delta 2 is the detuning of laser 2 from the transition 2 to 3.
Okay, so you simultaneously apply two lasers.
You apply 2 laser fields which are addressing this system. Okay. Of course, you could also say, well, laser 2 could have some perturbation on laser on ground state 1, right? When I apply a laser to a system, of course, it addresses all the transition. So assume that there's some selection rule between, say, 2 to 3 that doesn't let laser 2 drive transitions from 1 up to 3. Okay? So that is indeed a good question, because I have sort of said that laser 1 only addresses 1 to 3 and laser 2 only addresses 2 to 3. But if there are not good selection rules, or if you pick the frequencies wrong, then you might have this guy also that could be nu2 with some omega prime 1, right, which drives this transition as well. I'm ignoring those terms because of selection rules or something, just to make it simpler. You can always make this more complicated. Okay. Right. So what happens in the rotating frame? What intuition do you have for what the system Hamiltonian should be in the rotating frame and the rotating wave approximation? How do I start thinking about this problem without actually solving the entire set of equations? Reason by analogy to the two-level system. So if I had two levels, 1 and 2, and I put a laser on and frequency nu1 with delta 1 as the detuning, right? What did it look like in the rotating frame? What is the Hamiltonian like in the rotating frame? What did I say? What happens to the level 1 in the rotating frame?
Would become omega 1 minus mu 1.
Right. Which means it's splitting from the state 2 will be omega 1 minus nu 1, right?
Yeah.
Which is delta 1, the detuning. So remember I said that in the rotating frame I have two new states, 2 tilde and 1 tilde, or 1 tilde and 2 tilde, I can never keep them straight, which are split by delta. Remember this? Yes? Everyone okay with this? You should be by now. You've seen it several times. Okay. And of course, there are transitions between 2 and 1 that are governed by omega, the Rabi frequency. So the Hamiltonian of this system was just 0 omega star delta, or omega star over here, delta over here, whatever. Okay, with 1 over here. And maybe there are minus signs. Okay, forget about all that for a second. So by analogy then, what will this system look like? You have now 1 tilde, 2 tilde, 3 tilde. What will this splitting be? Come on.
Delta 1.
Delta 1. That's all. It's not a trick question. And 3 to 2? Delta 2. Okay. So now, and again, if I take the 0 of energy to be 1, H now will be minus H bar delta 1 times 3. So the state 3 from the 0 of energy has a splitting delta 1. Sorry, the minus signs are having to change everything, but which it's easier just to. And then the difference of energies between 2 and 1, right, is delta 1 minus delta 2, right? So the state 2 is at this energy in this rotating frame. This guy is given a special name which is called the 2-photon detuning. Okay? And it's clear why, because it just represents the difference between the two laser frequencies. And then you have to have the driving terms. So you have again omega between 1 and 3, or omega 1, and this is omega 2, which drives between 2 and 1. So we write those terms down. 1, 2, 3 and 1, plus Hermitian conjugate, minus h bar omega 2 over 2, 3, 2, plus Hermitian conjugate. And so if I wrote the matrix for this system, or if I write the set of equations, C1 dot, C2 dot, C3 dot is equal to this Hamiltonian, it will be 0, 0 minus h bar omega 1 star over 2, h bar delta 2 minus delta 1 minus h bar omega 2 star over 2 minus h bar 1 over 2 2 over 2 and minus. Okay, times of course C1, C2, C2. In my first approximation, or the first case that I'm going to consider, is a situation where the 2-photon detuning is 0. Okay. Which doesn't mean that 1 and 2 are degenerate. It just means that the system is being evolved according to just the state 3 and 1. So choose the 2-photon detuning, delta 1 minus delta 2, to be 0. So I take the two laser frequencies. I may still detune them from the state 3, but the two of them together are on resonance with respect to the 2-photon resonance, or the transition between 1 and 2. Then the Hamiltonian is just minus h bar delta 1 3 3 minus h bar omega 1 star over 2 3 1 plus minus h bar omega 2 star over 2 3 2 plus Hermitian one. And we can diagonalize this. That's basically that Hamiltonian with just this term set to 0. Okay? The term. And this guy, if you find its eigenvalues and eigenvectors, has 3 eigenvalues, right, as expected. E0, which is 0, E plus minus 1, which is minus h bar delta 1 over 2 plus or minus h bar over 2 square root delta 1 squared plus omega effective squared, where omega effective squared is equal to square root omega 1 squared plus omega 2 squared. Okay? Maybe there are factors of 2 and 4 that I might get wrong, but you can easily find this on your own. Okay? And the Eigen Values, there is a state 0. State plus minus Okay, just straightforward diagonalization of that matrix with delta 1 minus delta 2 set to be 0. Well, let's look at this set of eigenstates and eigenvalues because this is very interesting actually. Okay? So the first thing we notice is the state 0 has no admixture of the state 3. Okay? So the state 3 does not present in this eigenstate 0, it's a pure combination of the state 1 and 2. Okay? Now because of this, what it means is, I mean, so far we have not considered this, but imagine that this was some excited state of an atom, right? And if you prepare the system in the state 2, in this particular state, 2, 1, because it has no admixture from the state 3, which for example may decay to state 1 and 2, we see that you can live forever in this state 2 and 1. But notice it's a funny state, it's only present under the effect of the lasers, omega 1 and omega 2. So this is an interesting state. So what is it actually doing? So let's look at that. Can I erase this? All of this? Yeah, I think I can erase this. Okay. We'll keep that one, that picture there. If you look at the action of the Hamiltonian on the state 0, you find it has 0 eigenvalue, right? Right? What does that mean? Means that the Hamiltonian does not affect the state 0. You can evolve the system under the action of these two laser fields, omega 1 and omega 2, and the system will never go out of the state 0 because it's always at eigenstate 0. Okay? There's no phase, nothing. Just stays there. Okay? And you can verify this easily, right? You can put the terms that are important. So obviously the state 3 is not present in this. So when the Hamiltonian acts on this guy, 3 will not have any terms that act on this. And then the terms that go here, 3, 1, right? So you can easily show for yourself that the terms that are, say, omega 1 star 3, 1 plus omega 2 star 3, 2 plus the Hermitian conjugates, right? Those are the only terms, the ones that have 3, 1 and 3, 2 in them that could affect the state 0, which goes as omega 1, 2 minus omega 2, 1. I'm ignoring all the sort of factors and coefficients because they don't matter. You can easily show this goes as minus omega 1 star omega 2 plus omega 2 star omega 1, which is equal to 0 for any real omega 1, omega 2. So again, I just verified that. But I explicitly now I'm showing you that the action of the laser fields by these driving terms, which are these driving terms omega 1 and omega 2, does nothing to the state 0. Okay? The state does not talk to the laser fields at all. Okay? Even though the precondition for having it was to have two laser fields in the system. So this is what we call a dark state. Okay? Because an atom that is prepared in the state 0 will never be excited to the excited state 3. Okay? Or out of its state, this superposition. And because it has no admixture from the excited state, it is immune to spontaneous emission also. This we often refer to, there are more advanced versions of these which are called decoherence-free subspaces when we come to like quantum information processing. Because it's basically immune to any kind of dissipation or decoherence of the system. The only thing that could cause it to have a problem is if 2 and 1, maybe decohere from each other. Like maybe there are other factors, like 2 and 1 maybe talk to some phonons or something else in the system that causes them to decay. Okay? So if 2 and 1 are not true eigenstates, but maybe they have some relaxation to other states out there, then of course, then this is no longer valid. But as long as that doesn't happen, if these are truly long-lived states, the action of the electromagnetic field has no effect on them. So why is this so interesting? Okay, how much time do I have? Oh, I'm out of time. Okay, very quickly then, I'll just tell you why this is interesting. Which is, if I prepare the system in the state 0, okay, and let's imagine for a second, so let's imagine for the initially, let's say that I'm in the state 1, okay? Okay? So at time t equal to 0, I prepared the system in the state 1. If you look at this guy, and if omega 1 is 0, right? If I make omega 1 very, very small, and I slowly turn on omega 2, you see that 0 and 1 are nearly identical. It's just like the adiabatic passage idea, okay? So initially then, when omega 1 equal to 0, so omega 1 equal to 0, the state 0 is identical to the state 1. Okay? When omega 1 is 0, but omega 2 is small but non-zero. And then as time evolves, as omega 2 not equal to 0, right, I go into the state 0, which is now has the omega 2 sitting in front of it. Now I can turn on state omega 1. Now I turn on omega 1 not equal to 0. I bring in the admixture of the state 2, while I simultaneously make omega 2 go to 0. And you see, as omega 2 now ramps down, going to 0, this component vanishes, and this guy becomes all into the state 2. So I started in state 1, okay? I slowly ramped up the field omega 2, which made the system into this linear combination. And then as I turn on omega 1 and make omega 2 go to 0, this state goes into the other state 2. I've accomplished the adiabatic passage from 1 to 2. Okay? Without ever going through 3. Okay? And that means that this is very robust against spontaneous emission and all those other factors I mentioned. Because otherwise you would think the way to accomplish the transfer from 1 to 2 is to go up to the state 3 and come back down via the laser field. This would be the intuitive thinking for what you should do. There's another non-intuitive thing about this. Look at the sequence that I just sketched for you. The sequence starts by applying, so initially remember the population was all in state 1. Intuition would say apply omega 1 first to take it up to the state 3, and then apply omega 2 to take it down to the state 2. This would be a simple pulse sequence you could come. My pulse sequence here is non-intuitive. I start with omega 2 not equal to 0. So I turn on this guy. So it's omega 2 that I turn on, which is addressing a transition where there is nothing. There's no population there. Okay? So even though there's no population, I turn on omega 2. Okay? It seems to do something to the system. We'll consider what that might be. And then after I get to some point, which of course you have to fine-tune that a little bit, I can then turn on omega 1 and turn off omega 2. So it's kind of interesting, right? Because I don't do it the intuitive way, which is to first turn on omega 1, then turn on omega 2. I turn on omega 2 first, and then as I'm turning it off, I turn on omega 1, and that gives me this so-called non-intuitive pulse sequence. This is also called stimulated Raman adiabatic passage. This is the famous sort of pulse sequence. It's called STIRA, stimulated Raman adiabatic passage. We can understand the adiabatic passage part. We already considered adiabatic passage for a two-level system. The reason it's called Raman is because this kind of lambda level system is often used in Raman spectroscopy or Raman effect to consider what happens. It was originally sort of understood by Raman for the Raman effect. And so now all of these systems sort of go under the category of Raman systems. And the stimulated is because, as I said, we're applying this non-intuitive pulse sequence. We're somehow making the population go from 1 to 2 by first applying the omega 2, then applying omega 1. And I'll sketch these out in the next class, more detail. It's not very complicated, I'll show it to you. Okay. So I'm going to show you actually the simulation of it. I'll do that in the next class. Any questions? Sorry? Before I... Yeah, you have a question.
You slowly turn on the omega 2.
Yeah.
So what do you mean like you slowly?
Well, in the same way in which we have to worry about adiabatic passage in the two-level system, I'll just show you. So if you plot the eigenvalues, like remember, here we plotted the eigenvalues epsilon plus and epsilon minus for a two-level system. You can do the same thing for this system, which I was going to show you in the next class, but I'll just show it to you.
Okay.
Which is, if you look at the eigenstates, there's a zero state which doesn't change in energy, and then there's a state 1 and 2. If everybody can see this. This is the states 1 and 2 are E plus and E minus, right? Just E plus and E minus, which are over there. They will have this kind of behavior under the adiabatic passage. So we want to make sure that the rate at which we sweep from left to right is slow compared to this splitting over here. Okay, I'll come back to this in the next class. So the same argument as we did for adiabatic passage in two levels.